Hello everybody, I'm going to show the solution to a system with infinite number of solutions that uses an augmented matrix, and in addition to showing how to get the reduced row echelon form to the augmented matrix, I will also show how to write the solution in different formats. So we have a system of equations. Supposedly this is the augmented matrix of that system, and right now what's missing here is this vertical line that separates the numbers of the coefficients from the left hand side of the equations from the right hand side constants. So let's write this vertical line, and we have 7 columns altogether. The right hand side numbers are on the very rightmost column. So the other columns represent variables. If we have many columns, many variables, then we better number them instead of using notation x, y, z, w. So numbering usually starts with x1, x2, x3, x4, x5 and x6, and this augmented matrix is now in an echelon form because it's upper triangular. We can also notice that already the leading entries in the rows are ones, but although this is in echelon form, but it is not in reduced row echelon form, because in reduced row echelon form we're supposed to have zeros above these leading entries. So the leading entries that I boxed are the so-called pivot entries, and we're supposed to make all the entries above them 0. So right now we have this, and this 3 entries above the pivot entries that are not zeros. So basically we get this kind of augmented matrix in echelon form when we do the first part of the Gauss-Jordan elimination. So the second part is when we go backward from the bottom to top. So first of all, if we denote this as R3, row 3, row 2, row 1, then we get the new row 2 by adding to the present row 2 minus 2 times row 3, so that minus 2 cancels plus 2. So this is minus 2 row 3. Actually, the way I like to do this, which is kind of how the computer does it, that you add minus 2 times row 3. So we are always adding. We don't just change the sign plus or minus. The computer will know that we always have to add, but we have to add the opposite sign, minus 2 times row 3. All right, so then row 2, we write this down, 0, 0, 1, 9, 2, minus 3, minus 4, and then this is row 2, and then minus 2, row 3, 0, 0, 0, 0, minus 2, 8, minus 14. And then we add these together. So 0, 0, 1, 9, 0, 5, minus 18. This is the new row 2. And then we get a new row 1 if we add minus 9 times row 3 to row 1. Right, so let me write this down also. Row 1 minus 9, row 3. First row 1, just copy down 1 minus 3, 9, minus 3, 9, 7. And then the right hand side 6. And minus 9 times row 3, 0, 0, 0, 0. Minus 9 to make 0 with the 9, then 36 and minus 63. And then again we add these together, these two rows, to get 1, minus 3, 9, minus 3, 0, 43, and minus 57. So this is new row 1. Let's write down where our matrix is currently. The new row 1, 1, minus 3, 9, minus 3, 0, 43, minus 57. The new row 2, 0, 0, 1, 9, 0, 5, minus 18. And row 3 that doesn't change, 1, minus 4 and 7. All right, so let me box again the pivot elements. Above this pivot now we have all zeros, and then the only thing is left to eliminate this 9 above this second pivot. So for that we have new row 1 as row 1 plus minus 9 row 2, which means 1 minus 3, 9 minus 3, 0, 43 minus 57, 0, 0, minus 9, minus 81, 0, minus 45, and this is plus 162. And again we add these together to get 1, minus 3, 0, minus 84, 0, minus 2, and 105. With this we get a so-called reduced row echelon form for the augmented matrix. 1, minus 3, 0, minus 84, 0, minus 2, 105. Second row 0, 0, 1, 9, 0, 5, minus 18, and then the third 0, 0, 0, 0, 1, minus 4, 7. So let me mention that why the echelon form is not unique. This reduced row echelon form should have a unique form. There is only one of them, where all the leading numbers are ones, the pivot, and under and above them everything is 0. And let me also write this vertical line to separate the right hand side from the left hand side numbers. Here we are with the reduced row echelon form. We're supposed to be able to read the solution from this one. The problem is that because we don't have unique solution, we have infinitely many solutions. How do you write this down? Again, we start from the bottom, writing the solution usually. So again, these are numbers corresponding, columns corresponding variables x1, x2, x3, x4, x5, and x6. So this last row corresponds to equation x5 minus 4x6 equals to 7. And what we do is we solve for the pivot variables, the variables that are in the pivots. So if we solve this for x5, we get x5 equals 7 plus 4x6. And then what do we do with x6? Well, one simple way to write x6 is that this is just x6. It's called a free variable, which means it's arbitrary. Hence, we have infinitely many solutions since x6 can be chosen to any number. And once you choose one number, you get one x5 corresponding to this x6. And then if you change x6, x5 will change. All right, so going back from the last row to the second row, we have this one corresponding to x3. So x3 plus 9x4 plus 5x6 equals minus 18. And again, we solve for the pivot variable. x3 equals minus 18 minus 9x4 minus 5x6. x6 we already know that it's a free variable, and now we have another free variable, x4 equals x4. And then we go to the first row that has x1 minus 3x2 minus 84 x4 minus 2 x6 equals 105. And again, other than the variable in the pivot column, all other variables are free. We're supposed to rearrange them to the right hand side. We have 105 plus 3x2 plus 84x4 plus 2x6. We already know that x6 and x4 are free, and now we also have x2 as free. For example, WebWork expects you to enter the solution as x1, x2, x3, x4, x5, x6 equals, and then for x1 you enter whatever you get in terms of x2, x4, x6. For x2 you just have to enter x2, and of course the index is not accepted in WebWork, so you really have to actually write it as x2 next to each other. For x3 we write the formula. Then for the free variable x4 we just write that x4 since it's arbitrary. Then x5 we have a solution in terms of x6, and x6 is free variable. So this is the way you can enter the solution in WebWork for this kind of problem, for example. And we have altogether 3 free variables, not just one, but it kind of doesn't matter. It's in any case infinitely many different solutions. Whatever number you choose for x2, x4, x6, that gives you one solution, and then if you choose another set of numbers for x2, x4, x6, you get another solution. Another way to write this solution is to write this in a parametric format. So sometimes students are confused to write that x2 is x2. What does it mean? It really means that it's free. Maybe a nicer form is to write to use a different parameter, not x2, x4 and x6, but use different variables. For example, to write that x2 is maybe p, x4 can be s, and x6 could be maybe written as t, and then write that p, s, t are arbitrary. And also sometimes you write the solution in a solution vector in column format. x1, x2, x3, x4, x5, and x6. Yeah, in print, of course, this is not very convenient because it takes up a lot of space. So row vectors are usually written in printed books, but column vectors are nice visually, in my opinion. So first, let me write this down entry by entry, what x1 is, starting with maybe the constant 105. Then we have 3x2 is now 3p plus 84x4 is 84s, and 2x6 is 2t. Then for x2 we have that it's p, x3 we have a long solution for x3 minus 18, 9x4 minus 9x4, so this is minus, let me write it under the s since x4 is s, minus 9s, and minus 5t. That x4 is just s, x5 7 plus 4 x6, so x5 is 7, and then 4t, and x6 is just t. So I can write this down, of course, next to each other, but in the next step what I want to do is I want to separate into separate column vectors these parts of the solutions. So then this way we can write 105, if there is no constant, then it's 0, minus 18, 0, and then 7. And then what happened? We have missing here maybe a 0 actually for the constants. Then for the p's we have 3p, p, and then nothing. For the last 4 entries, we have 6 entries in each column. Then for the s's column we have 84s, 0, minus 9s, s, and then 0, 0. And then for the t's column we have 2t, 0, minus 5t, 0, 4t, and t. And finally, a nice thing to do is to factor out these p's, s's, and t's from the vectors and write this in a vector format. We have a constant vector, then we have p multiplying the vector 3, 1, 0, 0, 0, 0, s multiplying the vector 84, 0, minus 9, 1, 0, 0, and finally t multiplying the column vector 2, 0, -5, 0, 4, and 1. And maybe in the future we will talk about what exactly these column vectors mean.